Hello, my name is Zhang, a PhD student from Iowa State University. My topic is on failure diagnosis of the storage stack. Storage system failures are troublesome. They may result in data loss, service downtime, or other consequences. There are many existing efforts for storage system failures. Most of them focus on testing. However, testing tools usually require special testing environment, such as a customized kernel, and they cannot prevent all failures. Therefore, failures may still happen in practice. So, what can we do if a failure happens in practice? Typically, we rely on diagnosis tools to analyze the root cause of the failure. For example, GDB can set breakpoints, system type can trace kernel functions, and the SCSI bus analyzer can intercept the device commands. However, using these tools for diagnosis may require substantial manual efforts or special hardware. More importantly, each of them only covers a portion of the storage stack. In other words, none of them can generate a whole picture of system activities for diagnosis. Due to lack of tool support, diagnosing failures is often challenging and time-consuming in practice. One real-world example is a failure incident at a Gatla data center where the server crashed and the file were corrupted for unknown reason. Developers spent 2 weeks just isolating machines and restoring data. After weeks of diagnosis, Samsung SSDs were blamed for the failure mistakenly. However, 1 month later, a Linux kernel bug was identified as the root cause. The failure involves complex interactions across the storage stack, which inspire us to design a Crosslayer approach. Based on the observations, we propose a Crosslayer approach called X-ray. X-ray has 4 advantages. First, it supports a modified software stack. Second, it intercepts device activities without relying on kernel or special hardware. Third, it can visualize multi-layer correlation. Finally, it narrows down root cause semi-automatically. The platform has 3 parts. The first part is host agent. Host agent captures kernel and application information. It can help understand the high-level semantics of system activities. The dev agent captures device commands in the virtual machine without relying on the OS kernel or special hardware. It can help understand the changes of persistent states. X-Explorer can facilitate diagnosis in 2 ways. First, it builds and visualizes a correlation tree. Second, it can highlight critical nodes or paths based on rules. Due to time limit, I'll skip the details, but let me highlight 2 key challenges. First, how to correlate information across layers. We cannot use SCSI or NVMe hints because they require modifications to the application or kernel. Instead, we collect timestamps at different layers and align the events based on timestamps. We use NTP to sync the timestamps inside and outside of the virtual machine to avoid inaccuracy caused by virtualization. Another challenge is how to reduce manual efforts. We come up with 2 ways. First, in order to make log more intuitive, we visualize the cross-layer events and dependencies in a correlation tree. Also, we can apply rules to prune the tree and narrow down the root cause automatically. There are 2 ways to define the rules. First, the user can specify the rules based on domain knowledge. For example, ancestors of device commands may be suspicious, so we may highlight the relevant nodes as a critical part. The second way is to use a reference execution. Failures may or may not occur due to different environment. We can leverage this non-determinism to find a reference execution, then do comparison and get the difference part. Okay, that's the basic idea of our approach. Let me show some preliminary results. First, let's see a failure case reported in the literature. In this case, a kernel bug is manifested as serialization errors on SSDs. We applied X-ray to analyze the failure. The left figure shows a correlation tree, which includes 3 types of nodes, including system calls, kernel functions, and device commands. The right figure highlights the root cause of the failure, which can be identified using X-ray quickly. Please refer to our precision paper for more details. We have studied 5 failure cases in total. The table summarizes our results. For each case, The numbers in the table means the node count in the original tree and the remaining node count after applying one of 3 simple rules. We can see that the rules can help reduce the search space for root causes effectively. On average, we only need to analyze less than 5% nodes of the original trees. This is a huge reduction of manual efforts. In conclusion, we have shown a cross-layer approach called X-ray for diagnosing storage failures. We will explore more real-world failure cases, derive more diagnosis rules, and automate the comparison based on the reference tree. Thank you. Any feedback or comments are more than welcome.